So first, I want you to start thinking about temperature a little bit different. So how I do this is I start out with a little experiment. So if I tell you in Europe, I would say 20 or 30 degrees, everyone seems to know what that is. Or if you're in North America, if I said 70 degrees or 85 degrees, everyone knows what that is, right? Okay, so I want to do a little experiment. So what you to do is just hold out your hand and tell me the room temperature. You can write it down in a little Q&A. You can write your answers down there. But the real answer is, it's hard to tell. If I tell you 75 degrees or 22 degrees, everyone knows what that is. But if I ask you to quantify it, it's hard. We're not really good thermometers. And another way the next step we're going to do, the next little experiment, is I want you to touch two different objects. So like I've got the metal leg on my chair and my tabletop, my wooden tabletop, desktop. Don't touch your computer. Christopher's got a piece of metal, a wrench, and a piece of wood. Now, I want you to ask which one is colder and which one is warmer. Okay, someone's got to type an answer in there.
I think I know the answer, but let's see. Here we go. A chair leg in the
chair leg, the metal. Yeah. Someone says the chair leg's colder, and someone else says they're the same, and that's exactly correct. No, they're both exactly the same temperature, but one feels colder than the other, and that's because when we grab the piece of metal, it pulls more energy out of it. It's called convection. So that pulls more watts, more energy out of us. So our brain says that's colder. I can't tell you the temperature, but it makes me feel colder. Where if I grab like a piece of foam, it's not pulling much energy out of me. So my brain says that's not going to make me colder, so that's not cold. And then if I grab my tea, it's putting energy into me. So my brain says that's warmer. So when you touch something hot, we can't say that's 50 degrees or 80 degrees. We just know there's a lot of energy coming in. So the point of this is we all think in temperature, but really what we really feel is the energy transfer, energy coming in and energy coming out of our bodies. Metal, more energy is coming out, so our body says that's colder. And more neutral, we say it's not very cold, and hot is energy coming in. And that's actually watts. That's measured in watts. So what we feel is watts coming into the body and out of the body. So it's a nice little thing. So those things, I'm not sure I explained it well enough. Two objects sitting in a room soaking up the same amount of energy, they're both the same exact temperature. So they're exactly the same temperature, but one feels colder. And that's because it's just pulling more energy out. So be careful now when you think about how warm or cold it is. It's not that relevant. It's more about what takes more energy out of you and or puts more energy into you. So that becomes more relevant again, and it's in watts what we really feel. So we feel in watts. So that becomes more important. Okay. So now, as a sports person, what is the main goal? Okay, someone can type this in the Q&A also. What's the main goal when you're competing?
Let's give us 15 to 20 seconds to provide some answers in the chat, just so we can see those. Yeah. Number one answer from Eric, don't overheat as the main goal.
That's good. That's good. Don't overheat. But some people will say it's to win. And what do you need to win? Get to the finish line before anyone else? Yep, that's correct. And how do you do that? You need one component. It's really simple. It is speed. If you have more speed than the other guy, then you get to the finish line first and you win. So we're always trying to get more speed. And for the sports that we're talking about, running, triathlon, cycling, swimming, it's always about speed. And what do you need to make speed? You need power, okay? And then a lot of us know, and that's what we measure in watts on our power meters on our bicycles. And then we know that if we spend a time optimizing our aerodynamics and our rolling resistance and mechanical efficiency, we can turn those same watts into more speed. Correct? This shouldn't be anything new to anyone, I don't think. So we know if we make that more efficient, those same watts turn into more speed. Okay, so what do we need now to make watts, to make power? It's pretty simple again, nutrition, calories. We need calories that get converted through our metabolism and energy and all the energy systems that turn into measurable output power. But then there's this thing called gross efficiency. It's basically how efficient a human is since turning the nutrition into mechanical power. And a good trained athlete's generally around 20%. And that's a good athlete. So to make so a gross efficiency of 20%, that means to make 300 watts to mechanical power that you can register on your power meter, it takes 1,500 watts or 1,290 calories per hour to make 300 watts that you measure. Okay, so 1,500 gets through all this stuff, only 300 turns into mechanical power. Okay, so in physics, energy can't be created or destroyed, only converted. So 1,500 to 300, that means there's 1,200 watts missing that equation. Any guess where that goes? The color kind of gives it away a little bit. It goes into heat. So the biggest thing an athlete produces is all those calories, almost all of it turns into heat in a sports environment. Okay. So what happens now is when your body temperature goes up, your gross efficiency goes down. And there's a lot of research backing this up. We've done some other tests to back this up. And it's generally about 1% per 1 degree C. So if your body temperature goes up 1 degree, your gross efficiency goes down 1%. Now, I'm going to explain what all that means because it's a little confusing. So let's just take this person who's doing a time trial or something, and he's starting with a core body temperature of 37 degrees, just normal. Did a warm up with a cool vest, so we pre-cooled. And so let's say his gross efficiency starts at 22%. And 22%, and now we're just talking about threshold power everywhere. So we're just going to talk about threshold power. So that means that with his 1,500, with his calorie budget of what he can do, that power output is 330 watts. Okay, that's threshold power. Now, he goes up 1 degree in body temperature. So he's just up to 38 degrees. It's not very much. It's 99 degrees or something, 98 points. It's just not even 100 degrees yet in Fahrenheit, and 1 degree in Celsius. And so the gross efficiency drops to 21%, 22 to 21%. Now we're doing 315 watts threshold power. So we just dropped 15 watts. Okay. Now let's say we go up to 40 degrees, which is high fever. And we see athletes do this very often. So now the gross efficiency has dropped 3%, which means now our threshold power has dropped down to 285 watts. Okay. So if our goal was speed, we just lost 45 watts. Now, 45 watts, most people know, is a lot. And it is a lot. And that's why, like recently, the year before, I was at 23 training camps because a lot of the pro cycling teams and a lot of other people are really looking at this topic now because they can see that there's a good gain that can be made here. So I'm just going to give a little recap. And so what can we do with it? So again, we did our example of 37 degrees core body temperature with 330 watts. And then when they got up to 40 degrees, they went to 285 watts. So we had a drop of 45 watts. Now, if we start to introduce training, which we call heat training, we can change that percentage and say, for example, it's no longer 1% per 1 degree C. We can change that to 0.6% loss per degree C. We actually change the slope of the line just a little bit, but mostly what we do is we move it across with the training. So instead of that 40 degrees, if we get more efficient, instead of 285 watts, our threshold power, we're now at 303 watts. So we just had another gain. And now the thing that we're going to be talking about again here, now let's add cooling strategies in. Let's add more cooling in and help so we don't get to those high temperatures. So again, we were at 40 degrees, but let's say we're only getting up to 38.7 now, which is still pretty high, but not as high because we're putting good cooling strategies in and cooling technologies. So instead of 285 watts or 303 watts, we're now at 315 watts. So instead of losing, you're always going to lose, but now instead of losing 45 watts, we've only lost 15 watts at threshold power. So again, what do we want to do is, why you get hot is because you produce power. If you're putting out 300 watts, then 1200 watts has to get out. We've got to cool that off 1200 watts to keep the homeostasis the same. So we see people getting to extreme temperatures, even in races like the Paris-Roubaix. It depends again how many watts you have, and then it's a physiological system to get rid of those thermal watts. So if you're not efficient at getting rid of thermal watts, you'll get hotter quicker. Or if the conditions are harder to get rid of those thermal watts, like it's hotter out, it's hard to get rid of those. So it's just another physiological process why you get hot, and it's a byproduct of producing power. Okay, now just a quick overview or rundown on how cooling works. So I like to think of it as a simple mechanical system. So when you get hot, your body vascular dilates the blood vessels close to your skin. So your body puts more blood closer to the skin. And if it's exposed to colder air, then that's going to cool off the skin and cool off the blood. But the best way is when we start to sweat, the sweat, which is plasma from your blood, comes out of your blood and comes out as liquid, and the liquid evaporates. It goes through a phase change, and during that phase change, it pulls in energy, so it cools off the skin. When you're starting to get hot, feel like your arms, and they'll feel cooler because that's it. And then that blood that's circulating close to the skin cools off and then circulates to the rest of the body. So I like to, again, think of it as a mechanical system. When you get hot, your blood goes to the skin, away from the working muscles, all to the skin, cools off, and then recirculates around to the rest of the body to cool it off. And if you can see, as blood's going to the skin, it's going away from the working muscles, or it's not as much available to working muscles because your cooling system and your fueling system are connected. Okay. Now, that's kind of the first part. That's just a quick overview on how we produce heat and how our body kind of gets rid of some of it. We'll talk a little bit more there. Now, I'm just going to talk about when we talk about heat and what we can do about it. I like to call there's three main areas. And the first one is awareness. So you guys here listening to us, that's the first step. And I think this is 80%. As soon as I had one of the teams I was working with, they said, you know what? The biggest thing you did for us is everyone's now thinking about it. The coaches, the athletes, the soigneurs, the mechanics, the DSs, everyone's thinking about how we're going to cool them off, how we're going to prepare for it, everything. That's where it all starts. Most of it's pretty simple, but still the first thing is being aware of it. And then once you're aware of it, then we can start making changes to improve things. And the second one is training. And this is probably the most important one. So what's happening when we race, we really race at an elevated temperature, but we're also often training at a lower temperature. So, but what we need to do is train regularly at an elevated temperature so our body gets better at it. I mean, so what's happening is you go to race and you're putting your body in a new stress, running at high temperatures for prolonged periods of time that it's not used to. And if it's not used to it, it's not efficient. So we need to put our body in that stress and our bodies become more efficient. And it's pretty easy to do this and working into a normal training program. So when you do heat training, this is what we call heat training, you get two main components. One is your body. It was one of the sports scientists we worked with, he called it vascular coordination, which I liked. And that's just basically your body getting better at just putting the right amount of blood to the skin and still keeping muscles going to the working muscles to keep that up. So you become more efficient that way. Your blood flow management gets much more efficient for cooling and producing power. And the second one, which is really important, is your body sees that basically you need to sweat more. So your body creates more plasma, the sweat part of your body. and it's a pretty significant amount. And so what happens if you have this balance of hemoglobin to plasma, and when your body says, I'm going to produce more plasma, then the hemoglobin and plasma balance becomes out of balance. So your body, to counteract it, increases more hemoglobin. So your hemoglobin volume goes up. The percentage usually stays pretty close to the same, but the volume goes up. So you're getting more hemoglobin that your body can use. And that's why sometimes they call it the new altitude training, which is incorrect. It produces some of the same results of more hemoglobin, but it does it in a completely different physiological way. But it's really this blood volume, and we're seeing really good benefits in lots of areas, even in cooler conditions. So what's heat-aware training? It's basically really easy. You just need to put your body in a thermal stress, and to do that. And that thermal stress is generally around 38.5 degrees or 101.3 degrees. But it's really, the temperature is not so critical. It's really getting up to max sweat rate. If we get up to max sweat rate, and then the next point is once you're there, then you got to hold it for a duration. And generally, depending on your coach, most of the research shows around 45 minutes to an hour. And depends on how your coach wants to do it. And that's basically just to put yourself in. Our bodies are really good at handling high temperatures for a short amount of time, but not very good for a prolonged period of time. So that's why this continuous duration, you can't do 15 minutes now and 15 minutes an hour later. It really has to be continuous. And that puts us in this thermal stress where we get the adaptation, more plasma built up, and be able to produce more power at higher temperatures. And then generally when you're doing heat training, you do it old school, you do it to heart rate. And this is done for a couple of reasons. And the main reasons is the adaptation is so fast that the power numbers, if you generally go to heart rate, people will notice after even like 3 sessions that the power numbers are coming up pretty significant at that same heart rate. And that's your body getting more efficient. And then how to get the heat in, there's lots of different ways, and we haven't seen, there's generally personal preference. It doesn't matter as long as we get up to this max sweat rate. And that's best way is usually people do it on an indoor bike with no fans on. Then you can wear indoors with extra clothes on, outdoors with extra clothes on, especially blocking the wind. So wind gear, high room temperatures. I know some people, they really swear, they think that's much better for them. It doesn't matter. Or just harder efforts produce more watts and you're going to get hotter quicker. So it doesn't really matter as long as we kind of do that. And there's just personal preference. And then how we see most people doing this is just integrating it into your normal training program 2 to 3 times a week to keep that thermal stress in. And some people will start the beginning of the season with a heat block, which is basically for 2 weeks or 2.5 weeks, we'll do heat training almost regularly basis. So just some examples of what heat training is. And a lot of people will do it on integrating their session on an easy day. So if you're doing a longer, so for an example, a longer, say the coach has prescribed 4-hour easy ride. So you can do 3 hours outside and then maybe come inside for the last hour and sit on the erg, no fan on, put a paint suit on, and just do it heart rate sub-threshold and just kind of stay there. It's generally lower stress on your muscles, but higher stress on your thermal regulation system. So we're just trying to stress that thermal regulation system. And then sometimes when you're doing a high intensity day, you're pretty much doing heat training already because you're up there, your max sweat rate. And if you can just keep it, so you did it 40 minutes at this kind of thing, you just prolong your session, ride up a hill or prolong that session to keep that same sweat rate. So you can do it in a high intensity, make it part of a high intensity also. So it doesn't matter how you do it, but it's easy to integrate into a normal program. It's a different stress. It is a stress. So, and then we often get asked about like saunas or hot baths. And where we've seen the best results is you really need to get hot while you're exercising so your body figures out this vascular coordination. And if you want to do sauna, we've seen is the best results are usually right after your session. So you do your heat session and then go hop in the sauna or hot baths and that kind of prolongs this and helps stimulate the plasma generation. And we had some people who also will do saunas even before a session, just to preheat and then do that if they're just doing a heat only session. Now, when we do talk about heat training, we also want to emphasize not to overdo it. It's the one area which you don't want to overdo. A lot of athletes, you tell them to do, coach will say do 8 minutes at 300 watts, and they're going to do 8.5 minutes at 315 watts. They're going to push themselves. But here, you don't mess around. So heat-related illnesses can take a long time to recover from, or you can even die. So the first thing you do when you're doing heat training is not to overdo it. And if you listen to your body, and if you get any signs of feeling extreme discomfort, dizziness, any kind of heat-related symptoms coming on, you just stop. It doesn't matter. The adaptation will come. You just stop. Don't worry about it. It's not a failure. Just come back and do it again the next day. And if you do overdo it, it's because it's a big stress. And what happens usually is like 3 days later, you just don't feel like strong and can do it again. And again, it's because it's too much. It's an overstress. So again, if you're feeling any symptoms, you just stop. We worked with an Olympic athletes for a different event, and they did the first day. They said they did heat training with the whole team, and they almost killed the guy. They pulled him out, and everyone else is fine. They did that, and then they just slowly did this over the next few days. And after 2 weeks, the guy was fully adapted. This was right before Tokyo, and he couldn't even imagine why he couldn't do it 2 weeks before. The adaptation is actually very quick. It's very quick. So don't ever be discouraged and don't overdo it. And also, once you build up this plasma, that's why we say 2 to 3 times a week, is you need to keep the stimulation to maintain that plasma levels. So that's why you want to continue to do and continue to add heat training into your program regularly to keep this blood volume up. Okay. Now, the last part on this that I'm going to mention is a lot of times people used to call this heat acclimatization. That's why we kind of changed the nomenclature and we call it heat training. And instead of heat acclimatization, now we call it environment acclimatization. So what we prescribe, or what we've seen good results, is if someone was going to Paris Olympics from a colder climate, the Australia, Southern Hemisphere, and they wanted to get ready, probably 3 weeks before, what we'll try to do is simulate the conditions they're going to compete in. So that's hot and humid, and they're going to go and start doing heat work in there, and then they'll start doing some of their workouts in there. So when the plane lands, they're already acclimatized to the environment they're going to compete in. They're already used to it. And we've had really good results of this. And the other reason we call it environment acclimatization is because we had people doing the opposite way too. We had cyclists coming from Central South America coming over for spring classics. And so they were, a couple of weeks before they came, they started going to refrigerators and with fans on and getting used to riding in the cold. So when they got off the plane, it wasn't such a shock for them and they could be competitive right away. So basically, it's heat training, and well, again, you just 2 to 3 weeks before your event, we can start simulating the conditions. So when you get off the plane, you're already adapted. Okay, so we talked about the 3 points. The first one was awareness. Second one's training, which we can see is fairly simple to do. And the last one is cooling. And this is where we're kind of going to talk about a little bit more now. So pre-cooling is basically when you're warming up, wearing ice vests, which we've seen, which was a huge part of the hour records that we were involved in the last couple of years. But we've seen this kind of there. That's not really new, but it's keeping your core temperature lower. So when you start, you're starting at a lower temperature. So you have that little bit more advantage. And then post-cooling, this is a little controversy, how much it is for recovery, but there's easy ways to do this. But the hard one is during event cooling. And this is the one that's really hard because especially amateurs, they don't have DSs and team cars to come back to grab ice bags and other things. And even to come back and grab them is a lot of work. So what happened is for during event cooling, we got so much feedback and requests that said, look, we just need better solutions. What can we do? So we've done a lot of incremental stuff, but since I had so much inquiry on this, started looking at this from an engineering point of view and different solutions out there and different opportunities. And then that's how we kind of came in this. So let's just talk about during event cooling. And again, this is the kind of the crux of what we want to really address. Besides, we want to do better pre and post cooling, but during event cooling was where there's a big opportunity for lots of us. So I just want to show how energy was used and dissipated in an hour record. So I won't say which one this was, but I'll say it was pretty impressive. So the graph here, the white is the mechanical power that was used in the graph, and the red is the thermal energy that was produced. And this athlete was top of the top with a gross efficiency of just under 21%. So, and we had a couple of different ways we measured all that. So now this thermal energy, all the red part is in this next pie chart. So if we want to look at it, so what happened to that, all that thermal watts? 10.3% or 10.35% got absorbed into the body and turned into body temperature that went over 40 degrees. 40, yeah, well over 40 degrees. So he got really hot. Okay. Now, 17% of that energy was cooled off by the airspeed and the air temperature. So this person was at high airspeed, and so there was what we kind of call convection cooling, the wind. So that was 17% roughly. So that meant the energy, most of the watts that were lost was in evaporation cooling. And that was his sweat coming off, evaporating and cooling his skin. That's how most of the thermal watts got dissipated in his body. So if you can see, and then if we were going to do an event where they're not doing a world record hour, that 17% is going to be a lot smaller. And if you're running, that's going to maybe be 5 or 6%. And most of it will be evaporation cooling. So evaporation cooling, when we're looking at all this, is really the most important part for the cooling. So, and again, all that stuff is, just a reminder, is making the skin colder, and that's making your blood colder, which is cooling you down. That's how the energy transfer is going away. So we got to make that skin colder. And that cools down the blood, which cools down the rest. Now, evaporation cooling, what we said is the most effective. Now, what happens is you can lose a 1 liter of sweat is 628 cooling watts. When you go through the phase change, it takes about 628 watts of energy. Okay. So we have people doing hour records, they sweat over 2 liters in 1 hour. So that was, that's 1,450. I'm sorry, 1,250 watts that they would have got rid of. So and that's in 2 liters of water. So you can say that water evaporating is one of the most effective ways to get rid of thermal watts. And 628 watts per liter. So with all that, that's when we started this project, was to look at how we can do better cooling solutions. So when we kind of looked at this from an engineering perspective, the first thing we discovered is evolution did a really good job. Skin works really well. And especially with this evaporation cooling. So when we started looking at what we were going to do, is we said what we want to do is complement the skin functions. So nothing rocket science. There's no magic. There's no magic in any of this stuff. It's only incremental stuff and kind of very basic physics or simple physics is what we can do. So one is we want to minimize the effect. The first thing to do is minimize the effects of garments and accessories that prevent cooling. So what that means is the first thing is let the skin do this job and try not to block it as much as possible. So when we put a helmet on, we're blocking the airflow. So that's deteriorating from cooling. So we want to minimize some of those effects and think about that in the designs and the materials and other things that we're using. So the second one was increasing surface area. Increasing surface area is one of the easier ways. And that's why we started looking at like the handlebars or looking at other areas or the triathlon cockpit. because this is a bigger surface area that we can turn into a cooling heat sink or a cooling area. Basically, we're dinosaurs with the big fins on their back. That's increased surface area for cooling, and that's what we need to do, or that's one of the ways we can also increase that. And then it's also what we want to call is complement the sweat reservoir. So if we can complement that, if I can put a liter of water on me and have it evaporate away, that's 1 liter. My body doesn't have to sweat as much. So it's complementing that sweat reservoir. And that all that water comes in is potential energy. Potential energy is 628 watts per liter. And the last one is radiation input and output, but it's the smallest one and probably one of the more harder ones to do. So we're not going to, we are working on some stuff there, but we're de-emphasizing at the moment. And again, the sweat water evaporation, this phase change is what's going to cool the skin and cool you off and get rid of those thermal watts. So when we started looking this, that's why we started with a glacier tape, because that was great surface area. And this was kind of our proof of concept product. We were working with some new materials, and we have a patent in this. Is basically you've got this bigger surface area, and that's why it works so well. We charge it with some water and can recharge it while you ride with water, and then it's going to keep that cooling process going. And time trial cockpits. Some of you might have seen the project we did with Canyon and Ergon for Patrick Langer and Sam Ledlow, who both did extremely well. And that was just the first version. We've got some other things coming, some on our own and some with some partners. And then we're also looking at in apparel, where you can do micro surfaces and materials and actually increase the surface area of 10x of what our skin surface area is. So we've got some developments in there that we're going to be announcing in the near future with some partners that we're working with. That's surface area. And then the next one is sweat reservoir. And this is, again, some of the materials that we're using. We want to hold that water. So performance athletes, we need to charge the materials and the accessories with water for the cooling ability. It's not wicking. It's not anything. We actually want to retain some of that water. And you can see a preview of one of the products we have for running coming up. And so the materials hold a little bit of water, and then the magic is how we release the water for the right amount for cooling. And then we need the thermal conductivity, so that goes back to the skin. If I don't have that thermal conductivity, then that's cooling, but it doesn't really help us too much. So it's all pretty simple when you look at it, but it gets a little bit more complicated when you try and make it work. Now, one of the important things I want to talk about, which is a problem with us, is if you put an ice cube in the palm of your hand, when you first put it in, it feels really cold. But after a couple of minutes, it doesn't feel as cold. And this is because our brain, the way our brains work, is they normalize it and say, okay, I can see how much energy is coming out or how much watts it's pulling out of me. That's okay. It's not going to cool me down too bad. It's a little bit there, but I don't feel as cold as much. So the problem we have with some of our cooling things is you put them on, and Jay probably has the same problem. You feel it right away, but after a while, you don't feel it as much. It's because our brains normalize it. But if you take it off and you put it back on, everyone gets a sensation back. So there's a little bit of a problem there. Even though they're working and pulling these watts out, you don't get this huge sensation, but they're working. And that's the important part. And that's one of the parts that we're trying to communicate a little bit better, that they are working. And then when we look at cooling solutions also, we look at this really similar to aerodynamics, where in aerodynamics, like just talking for bicycles or time trial bikes, it's all the incremental pieces. I change my position, I put a better cockpit in, I put a disc wheel on, I put an aero bike on, I use a ceramic speed derailleur, or all it is really I choose the right helmet and the right suit, and it's all those little watts that add up to the aerodynamic savings. It's just not one thing. And this is the same thing for thermal. What we need to do is start looking at all these little places where we can start adding on little bits to get the bigger picture. And so a little bit from the helmet or the hats, a little bit from the clothes, a little bit from other areas. And so all those little bits will add up to a bigger bit that will increase your performance in the end. So with that, and so what we're doing now is we're working with some third-party labs in our own ways that we're testing this, so we're able to test all the different materials, because what our brand is really about is we want to be, in our DNA is we really want to make products that work. That's the kind of backbone of thesis of our DNA, is we want to add value. We want to, the coaches and the performance staff have the hard job of taking all technology and data and merging it together and with the athlete and the training program and turning it into results. So all we want to do is kind of remove there's a lot of bullshit in this area. And so what we're trying to do is only do really authentic solutions. And we're working with different OEMs also, where we're trying to provide real solutions that can actually help benefit the athlete to the end.